section 3.5, and before I go ahead and get started on this section, I want to recall a couple things that you can put in your notes or maybe off a separate sheet of paper. But I want to go over what we looked at in the previous section, the equation, or what the equation x equals 1, x equals 2, and x equals 0, what those look like when you graph them. So here is my Cartesian plane. Okay. If I were to graph x equals 1, that would be this line right here. 1. That would be x equals 1. If I had x equals 2, that would be this line right here. So if we know that x equals 1 is this line, and x equals 2 is this line, then x equals 0 must be this line right here. Okay. And similarly, if I had the equation, go to the Cartesian plane here, if I had the equation y equals 2, y equals 3, and then y equals 0, what would those look like? Y equals 2 would be this line right here. Oops. Y equals 2. And y equals 3 would be this line right here. So if that's true, then what would y equals 0 look like? Y equals 0 would be right here on the y-axis. Okay? So don't forget that as we go through this section here. Okay, so in section 3.5, we're going to talk about rational functions and their graphs, and we've been graphing a lot in this chapter. We graphed quadratic functions, which were the parabolas, polynomial functions, which were polynomials of degree 3 or more. And then now we're talking about rational functions. Remember, rational functions are quotients of polynomial functions. This means that rational functions can be expressed as a polynomial over a polynomial. Okay? And so P and Q are polynomials or polynomial functions, and Q cannot equal 0 because Q cannot equal 0. Because if we have 0 down here, this would be undefined. Okay. So the domain of a rational function is a set of all real numbers except the values that make the denominator 0. For example 1, let's go ahead and look at the rational functions. These are all rational functions that have a polynomial over a polynomial. Okay? And we want to find the domain of each rational function. So we're going to look at part A. The domain is what can x be, and we're also looking at, on the flip side, what x can't be. So here, if we look at this from A, we know x cannot be equal to 3. So basically, all numbers except for 3 would work. So we're going to go from, if we look at this number line, here's 3. Basically, every number will work on the number line except for 3. Okay, so we want to state that in rotation. That would go from negative infinity to 3. You don't want to include the 3, or from 3 to infinity. Okay. In part B, if we look at this denominator, we know the same thing as x plus 3, x minus 3. So x cannot equal negative 3 or 3. If we look at the number line here, then basically any number will work as long as it's not negative 3 or 3. So the rotation for that would be negative infinity to negative 3, or from 3 to infinity. Okay. The last one is, the last example, we don't want the denominator equal 0. So we don't want 8x squared plus 9 to equal 0. Well, no matter what I put in for x, when I add 9 to it, it's never going to equal 0. I can't factor this at all. So whatever you want to put in here, say I put 1 in here. 1 squared would be 1 plus 9, which is 10. If I put a negative 1 here, negative 1 squared is still 1. Then 1 plus 9 is 10. So no matter what I put in for x, it's never going to make the denominator 0. So this is going to be all real numbers. X can be all real numbers. So there's no value of x that makes the denominator 0. Okay. So on your own, go ahead and pause the video and find the domain for each of these rational functions, and then unpause it and check your answers. Okay, so here are the answers for A, B, and C. And I didn't draw the number line for each one, but feel free to draw this number line right here if you need help with an interval notation. Okay. Let's go ahead to the top page 134, and I'll talk about the most basic rational function, and that's called the reciprocal function, and that's defined by f of x equals 1 over x. So look carefully that we know that x cannot equal 0, so the domain is any x value except for 0. So let's go ahead and look at what happens when I try to graph this, and I'm just going to make a little table here. And eventually we're going to notice a pattern here, and we don't make a table, but kind of see what's going on with this function. So let's go ahead and start with, x can't be 0, so we're not going to use 0 here, because that would make us undefined. Let's start off with 1. So I have f of 1 would equal 1 over 1, which is just 1. So I get 1 comma 1. If I pick 2, I get f of 2 equals 1 over 2, which is 1 half. So 2 and 1 half, or you could do 2 comma 0.5. Do 4, you can do 3 if you want to, but I'll do 4. 1 over 4, which is 1/4, or same thing as 0.25. So I get 4 comma 1/4, and I get 4 and 0.25. But you notice that the x gets larger and the y gets smaller. It's getting smaller here. We can kind of keep this going here. You notice a pattern here. If I'd done say 5 or 10 or so on, this number will get a lot smaller. 1/5 is very small. If I did 10, 1/10 is super small compared to all the other numbers. And if I did 1 million, let's do 10,000, that would be 1 over 10,000, which is super small, almost close to 0. So if I had 10,000, I would get 1 over 10,000, which is very small. Okay, so I picked, I went to the positive direction for x. Let's go ahead and do, if I were to pick values like a half and so on, and I'm going to run out of room here, a little bit smaller. So if I picked, let's say if I pick negative values for x, let's do a couple of them, not too many. I would get the same thing, but I would just get the negative values. I would get negative 1 over 1, which is negative 1, negative 1. Here I would get negative a half. And this would be basically the same table I had before, but just the negative values. Okay, let's see what we have so far. If I were to graph 1, 1, it would be right here. And I also have 2 and a half right there. And I had 5 and 1/5. And so you see it kind of gets closer to 0. But you notice that no matter what I pick up here, if I picked a trillion, it'd be 1 over trillion. It'd be a very, very small number, but it'll never get 0, which just makes sense because we said x cannot equal 0. What we're going to do is we're going to draw something called an asymptote. And it's a dotted line because it's not part of my graph. x equals 0, what basically means is this graph is going to get very close to 0, and no matter how high my x value is, it's going to get very close there. It's going to be very, very small for y, but it's never going to touch or reach 0 for y. And then let's go ahead and look at what we have over here. On this side, I have -1, -1, so it's going to be this right here. And I have -2 and then a -1/2 right there. And if we continue that on, we would have had -5 1/5, and that would be right there. This y value here is never going to be 0. It's always going to be -1 over something, because I'll have something for x. Okay, so that's another thing we're looking at. Is we know that y will never equal 0. Here's another asymptote called asymptote. Okay, this is y equals 0. We make it dotted because we know that, and I have it messed up. My bad, I messed up here. This should be y equals 0. This is x equals 0. I just noticed that right now. So here we know y can never equal 0 and x can never equal 0. So that should have been up here. Okay. And so now let's go ahead and look at what's going on with the rest of the graph. What if I picked fractional value for x? So what if x were a half? What would happen right here? So x is a half. And if I let x equal a half, it would be f of 1/2 would equal 1 and over 1/1/2, which would be 2. So I would get 1/2, 2. If I let it equal 1/4, it would be 1 over 1/4, which is 4. And so on. So let's see what happens there. I have a half, and I get 2, so it'll be right there. And I have a 4th, and a 4 will be right there. Likewise, if we made these negative, I did -1/2, it would be the same thing, but I would just get -1/2 and then -2, and -1/4, it would be -1/4 and -4. -1/2 and -2, -1/4 and a 4. Okay, and that would be the most basic reciprocal function, or basic rational function, which is the reciprocal function. So I want to make sure I clarify something I got earlier. So I went ahead and drew this asymptote here because x can never equal 0. So I put a dotted line there to indicate that this graph will never touch 0. When you put that dotted line there, it just means that this will never touch 0. It'll be very close. And likewise here, and y will never equal 0 because no way to ever get this y 0. It's always going to be some number. And so I put a dotted line there because y will never equal 0. Okay. When you actually graph on an exam, you have this exact problem on the exam. You don't have to make all these points like I did here. What I would do is I would go ahead and do a couple major points. I would do the 1, 1, the -1, -1. I would do the 2.5, and then the -2.5. And then I would do the half and the 1/2 and 2, and then -1/2 and 2. So those are 1, 2, 3, 4, 6 points to use when graphing f of x equal 1 over x. Okay, so just use those 6 points. I want to do the other point to emphasize that the number gets smaller and smaller, and this gets larger and larger. And make sure you draw these asymptotes, and you got to label the equation like I did here, so I know which values you have there. Okay, so the video is about to end right now. I'm going to run out of time, so we'll go ahead and on the next video I'll start with another basic rational function, 1 over x squared.